just like air moves into and out of our lungs via respiration because of pressure differences, the oxygen and carbon dioxide also move from higher to lower pressures in our body. So they move down their pressure gradient via diffusion. And so we have two forms of gas exchange. We have alveolar gas exchange, where oxygen moves into our blood cells and carbon dioxide moves into the alveoli. And then systemic gas exchange occurs when oxygen moves into the body tissue cells and carbon dioxide moves into the blood. Hello, there we go. So Dalton's law, which is another gas law, states that the pressure of a gas is dependent on each partial pressure of the gases within of the individual elements within the gas. So each gas moves independently down a partial pressure gradient. And again, we're measuring all of these pressures in millimeters of mercury. The total pressure of all gases collectively is going to be what we call atmospheric pressure. And so atmospheric pressure has a lot of different gases. The majority of gas in the atmosphere is nitrogen. The gas that we all think about is oxygen, but there's all kinds of other gases as well. About 78% of the gas that we breathe in is nitrogen, but nitrogen doesn't tend to go into our blood. A very small amount of gas is actually oxygen. 21% is about oxygen, and then the remaining percent is the other different gases. And it's the oxygen that moves into our lungs because it's able to. And so here's another, there's the definition for Dalton's law, which I already mentioned. Another solubility or gas law is Henry's law. And it states that at a given temperature, so assuming temperature stays the same, the solubility of a gas in a liquid is dependent upon the partial pressures and the solubility coefficient. So nitrogen has a partial pressure of 597 millimeters of mercury. Oxygen has a partial pressure of 159 millimeters of mercury. This one must, or definitely has a higher partial pressure, but the solubility coefficient is basically stating how soluble, how easy it is for a chemical or an element to dissolve in a solution. Nitrogen has a very low solubility coefficient. It can't dissolve very easily, whereas oxygen can. And because of this, oxygen is going to be what moves across the membrane and dissolves in the blood. And carbon dioxide moves across and into the alveoli to be exhaled. So here at the respiratory membrane, we have a partial pressure of oxygen of about 104 millimeters of mercury. In the blood capillaries, we have a partial pressure of oxygen of about 40 millimeters of mercury. Oxygen is going to move down its pressure gradient from higher to lower concentration until it reaches about equilibrium. And carbon dioxide has a higher partial pressure in the blood than it does in the lungs, so it's going to move against or down its concentration gradient as well. In the blood tissues, so here's systemic gas exchange, we have more oxygen in the blood now than we do in our tissues. So oxygen moves from the blood into our tissues, whereas carbon dioxide has a higher pressure in the tissue, so it moves into the blood. Because nitrogen has a very low solubility level, it's not going to move into our tissues. But if we increase the pressure, we can cause nitrogen to become more soluble. So if we go down in pressure, like move from atmospheric pressure, we go lower, where we have a higher pressure, so underwater, that can actually cause nitrogen to be able to dissolve and goes into our blood and then can sit in our blood. And this can lead to decompression sickness if we don't move from the deeper environment of the water, of the ocean, of wherever we're at, up at a rate that allows nitrogen to diffuse out slowly. And so here we have our nice healthy lungs. And if we move down into the ocean, nitrogen moves from higher pressure to lower pressure in our blood. If we move back up slowly, allowing the nitrogen to leave our lungs slowly, leave our blood slowly and go through our lungs, then it's going to allow us to be healthy, to move back up, and we won't have any problems. But if we swim very quickly, say something happens to our oxygen supply or something, that can lead to decompression sickness. And so decompression sickness can cause blood vessels to burst. It can cause a lot of problems. Typically, treatment for decompression sickness is they're going to put you in a hyperbaric oxygen tank, and they're going to slowly bring your pressure back up, or back up to where it's supposed to be, so that the nitrogen can go out slowly from your system. And just kind of a cute joke, if any of you know who Chuck Norris is, which I think everybody does, when Chuck Norris is scuba diving and surfaces too fast, the ocean gets the bends. Get it? Ha ha. Okay, anyways. So how is gas transported in the blood? Oxygen, since it is very, it has good solubility, can dissolve and move in the blood as a dissolved substance. But the majority of oxygen actually binds to the molecule called hemoglobin, which is in our red blood cells. So 98% of our oxygen actually is transported in erythrocytes on the hemoglobin, and then the rest is dissolved. Hemoglobin containing oxygen is called oxyhemoglobin. If it doesn't have it, then it's called deoxyhemoglobin. Carbon dioxide, on the other hand, is really, really good at dissolving. It has a very high solubility coefficient, and so the majority of carbon dioxide actually is found dissolved as a bicarbonate ion. Very little carbon dioxide attaches to hemoglobin molecules. When it does, it attaches to the globin portion of the hemoglobin. So oxygen attaches to the heme portion, or the iron-binding portion of the hemoglobin. Carbon dioxide attaches to the globin portion of the hemoglobin molecule, or the protein portion. Hydrogen ions also will attach to the globin portion. And actually the binding of carbon dioxide or hydrogen ions to the globin portion causes hemoglobin to change and release other substances. So like if carbon dioxide binds to the globin portion, oxygen gets released. And so that's kind of how oxygen moves from the hemoglobin into our tissues, because it gets released as carbon dioxide comes in and binds. But because most carbon dioxide, when it moves in, it doesn't bind to the globin portion, what happens typically to carbon dioxide is it moves into the blood, into the red blood cells. It binds with water, producing carbonic acid. Carbonic acid then immediately dissociates into hydrogen ions and bicarbonate ions. The hydrogen ion is what binds to the globin portion, allowing the the oxygen to unbind and move into our body tissues. And then the bicarbonate ion leaves the blood vessel or the blood cell and goes into the blood plasma. When that happens, if nothing changed in our blood, we would end up having more electrolytes, negatively charged electrolytes than we need in our system, and that could cause problems. So chloride ions from the blood move into the erythrocyte, maintaining the electrochemical gradient. That's what I wanted to say, okay? And then once we get to the body tissues, carbon dioxide is going to be reformed. Bicarbonate moves back into the blood. Chloride moves out, so this is another chloride shift. Bicarbonate binds with the hydrogen ion that unbinds from the hemoglobin. And when that unbinding occurs, oxygen is able to bind. So oxygen comes in and binds. Hydrogen ions have to unbind. They bind back with the bicarbonate, producing carbonic acid. Carbonic acid then dissociates to the carbon dioxide and water, and carbon dioxide diffuses into the alveoli. I usually ask at least one question on this, so try to understand it, write it out, read it, and make up a way to memorize it, because it's not that hard, but you have to go over it multiple times to understand what's going on, okay? One of the clinical views talks about fetal hemoglobin. So we all know that the fetus gets its oxygen and nutrients from mom, but mom's hemoglobin has a high affinity for oxygen. If they have the same affinity for oxygen, then oxygen would never leave the mom's hemoglobin and move to the fetus through the placenta. So what happens is the fetal hemoglobin has a higher affinity for oxygen, which means oxygen will always move from mom's blood to the fetal blood, giving the baby what it needs. That can actually lead to jaundice. So jaundice is the inability to break down bilirubin. So when fetal hemoglobin, when the baby is born, the fetal hemoglobin has to be broken down, and adult hemoglobin is formed. If the liver doesn't have full function yet, then it's not able to break down the hemoglobin molecule properly. So when you break hemoglobin down, it produces this bilirubin, and bilirubin left in the system causes the yellowish tinge to the skin, but that's not the big problem. The big problem is it can cause damage to the brain. It can actually lead to brain neurological problems. Typical treatment for jaundice is going to be phototherapy. If it's a very minor case, then they will often tell you to put your child by a window and let UV radiation from the sunlight hit the child to help break down the bilirubin from the fetal hemoglobin. And that is all I have for you. So I'm going to turn this video off, and I will see you in Chapter 24.